Okay, so welcome to the last lecture of this course, that is influence of surface properties on mass transfer in small channels. Okay, though it is mentioned in surface properties, we will, as we are discussing in the last class, that uh, what will happen if we go for a sudden change in the flow area, that also we will take up. So there are, as I mentioned earlier also, there are few ways to intensify the transport rate of within a micro channel further or mini channel further. How? By inducing some change in curvature, that precisely what we are discussing in the last class. So as we say, there is this kind of disturbance waves are noted during the secondary flow. So and this is responsible for enhancing locally the mass transfer rate in the last one that we have seen. Then in this particular lecture, what I want to cover is that this two topics. Okay, how this sudden change in the flow path will enhance the mass transfer, and how this hydrophobic and hydrophilic condition may what more precisely or generalized condition we can say, sudden change in wettability of the tube wall can influence to produce the phase inversion, and how the phase inversion is influencing the mass transfer efficiency further, that we were going to discuss. So this is the setup uh, for for our very basics experimentation. So in this setup, we do have a view box, as you have seen in the very first tutorial. So we have the same thing that we have taken, toluene and distilled water. Only thing is that toluene mixed with 10% of acetic acid, and this acetic acid we are going to extract using the aqueous phase. That is the idea. So after they flow out from the test section, there is a separator where the phases are separated and taken out for further estimation of concentration of acetic acid in aqueous phase. Okay, so this is the idea. Then these are the test section that we have studied. First is 2 mm straight tube, 1 mm straight tube. Second one, third one, there is sudden contraction. So this is 2 mm and it is joined by another 1 mm tube. Okay, then this is just the opposite. This is first 1 mm followed by 2 mm. The idea is why we are doing this is when we go back to the literature, we have seen that people have used multiple series of sudden area contraction and expansion in order to enhance the mass transfer or mixing in miniature geometries. But there is a lack of systematic review of how much such change in areas you need in order to in order to really enhance the mass transfer, and how much energy you are consuming for that. So that is the motivation of doing this work, so that we can understand systematically that how much is going to utilize this particular change in diameter is going to utilize the change in efficiency. So this is, I guess, we have discussed a lot. Toluene water, 2 mm, straight capillary. So we have observed slug, we have observed droplet. Then for 1 mm straight capillary, we have, again, this is also we have seen that slug and the droplet. So their characteristic features is somewhat different. Then when they are when we are going back to the sudden contraction. So this is 2 mm upstream followed by 1 mm downstream. So now there is some interesting phenomena with respect to the hydrodynamics we have seen. So what we have seen that slugs that are formed in the upstream at 2 mm pipe is suddenly when they are exposed to sudden decrease of area, then what will happen to these slugs? They are suddenly getting elongated. Okay, and sometimes some droplets are also forming at the bottom, at the back of the slug. Okay, so this is the first observation. What will be the reverse observation when the 1 mm tube is followed by 2 mm? So that is sudden expansion of the flow path. So here we observe that it is the droplet flow in 2 mm that is dominating. Okay, so the droplet flow in 2 mm, when they found that 1 mm we have, let's say, slug, so one suddenly their diameter is increased, so these slugs forming well defined droplet in the downstream. So here is for the understanding and comparison. So this is 2 mm straight capillary, this is 1 mm straight capillary. You can see the entire range is dominated by droplets and very less slug. So here we have domination of slug. Then, so as I say that this is also 1 mm straight capillary downstream of sudden contraction. Okay, so you can see, so this is also 1 mm, this is also 1 mm, but this 1 mm is undisturbed, and this 1 mm is placed after a 2 mm diameter of pipe. So what is the difference? No droplets, precisely. What we have observed is a slug droplet, that is slug followed by a droplet. Most probably the droplet is formed from the slug tail itself, okay, detached from the slug tail itself. And most interestingly, for this 2 mm, when this is not disturbed, very less droplet flow, okay, but when it is placed after 1 mm 1 mm of pipe diameter, the entire thing is filled with droplet only. Okay, so this happens in the hydrodynamics when we have changes in area. So this is just a kind of observation we have discussed. Next thing is that in the last to last class, Professor Angeli has mentioned that there are different parameters that you can measure, okay, to estimate the mass transfer. One of them is extraction efficiency. So we have estimated extraction efficiency. So CAW O, that is concentration of acetic acid in aqueous phase at the outlet. This is inlet, so this is 0. This is equilibrium value and this is the inlet value. So this is the extraction efficiency for okay, so I mean for all the test section taking together. So what we have observed that the highest value of efficiency is noted for 1 mm. TS2 is 1 mm channel, straight 1 mm channel, followed by TS4, TS3 and TS1. So TS1 is 2 mm straight geometry. What is TS4 and TS3? Let us see from the test section. So TS3 is this one, sudden contraction, and TS4 is sudden expansion. So both the changes of area somehow contributed to enhancement of the extraction efficiency. But the highest efficiency is for this and the lowest is for this. Okay, now let us understand why this happens and how we can optimize or what type of geometry to choose. Okay, so for that kind of analysis, what we have done is that, so this is again viscous dissipation, but in this case, the viscous dissipation we have a ratio. Okay, so ratio of specific dissipation energy. So what is it? This is, so we have noted the least is for the straight 2 mm geometry, right? So what we have done, we have calculated this ratio. Okay, viscous dissipation for a particular test section, let's say TS2, TS3, TS4, all divided by TS1. What is the viscous dissipation in TS1? Why this? We want to understand, okay, TS1 is my least, TS1 give me my the least efficiency. I want to increase the efficiency. So what is the viscous dissipation is increasing for that? Okay, what is the increase of energy loss for TS2, TS4 and TS3? So here you can observe the TS2 giving you highest efficiency, but the viscous dissipation with respect to TS1 is the highest. Okay, followed by some kind of TS2 and TS4 are the points, but it is majority dominated by TS2 with having very high ratio of viscous dissipation, specific ratio of specific dissipation. Similarly, we also estimated effective energy efficiency. Okay, what is effective energy efficiency is this one. Okay, so what is this? This is giving you the idea that you have supplied the additional energy, uh, you are supplied the additional energy to your setup, to your test section to enhance the improvement in the efficiency or mass transfer coefficient. But how much of this additional energy is actually increasing the mass transfer coefficient, that is being estimated by this ratio. So it is the mass transfer coefficient of the particular test section by the mass transfer coefficient we got in TS1 divided by this one. Okay, excuse me, viscous dissipation of that particular setup divided by viscous dissipation of TS1. Okay, so idea is carried out the precisely what is your fraction of energy is going to enhance the mass transfer coefficient directly. Okay, so in this analysis what we got, we observed that TS4 is the is what that giving you the highest one. Okay, it is not TS2, because in TS2 the energy supplied is not fully utilized to enhance the mass transfer efficiency. Rather than it is viscous dissipation what is going to is giving you highest values in TS2 because of its reduction in diameter. So from here so you can look at these values. So the ratio of specific energy dissipation in a 2 mm straight tube. Okay, these are 5.47, 1.77, 1.74. Okay, so TS2 has the highest ratio of viscous dissipation, then followed by the similar values of TS3 and TS4. On the other hand, the values of this ratio of enhancement of mass transfer coefficient. Okay, so this is the least. So TS2 consume more energy, giving you a less value of increment for mass transfer coefficient. Higher values are noted for TS3 and TS4. So these values are close by, okay, for TS3 and TS4, and from here we have higher value for TS3. Okay, so what is TS3? Have you recall? Contraction, sudden contraction. So the idea gave you that you don't need multiple. Okay, even we need multiple, what type of change in area we should go for? Should we go for abruptly reducing the diameter to enhance the efficiency? So from this idea, we further try to simulate it to understand why in TS3 we are getting higher efficiency. What is the hydrodynamic reason for that? Because again it is the same thing. So the hydrodynamics is what is giving you controlling factor of the mass transfer, because they are giving you the specific area of contact as well as the residence time. So for that, we developed some CFD model of this sudden contraction, and we are using volume of fluid method to track the hydrodynamics. Then first, of course, is the model validation. Okay, after that, when the model is validated well enough with the slug length, and so this is where your image analysis will play a part that we have done the tutorial on. So you can compare actually, so this is kind of qualitative comparison on the upstream and downstream. You are ensuring, okay, they are same flow pattern we are getting. This is more of qualitative comparison where you are measuring the L/D ratio of the numerical slug and as well as L/D ratio of the experimental slug. So it is the experimental slug measurement where you need your image analysis information. Okay, now this is something interesting. So we have seen that in case of my flow through sudden contraction, a long slug is been noted. Okay, so if you recall for the flow pattern map, so what we have seen that is the formation of a long slug at when they encounter sudden contraction. But what we haven't seen or we haven't captured through the high speed camera is the presence of such kind of waves, that is disturbance wave generated due to sudden change in area from the vena contracta. And these waves you can see, so these are very close to the wall and they are giving you some circulation pattern. So there is a circulation happening inside in the film zone as well as the circulation are happening inside this slug zone also. So this due to this disturbance wave which a result from sudden abrupt change in the flow path are actually enhancing the mass transfer in the downstream. That is the otherwise it is the 2 mm, isn't it? And 2 mm straight giving us the lowest efficiency. It is due to this phenomena, the mass transfer efficiency of such kind of geometries are higher. Okay, so one thing is that, and second thing is that sometime there are some droplet formation also takes place. Okay, so that is not given here, but that is also happened. So what is this is the first part of the study where we have just seen that a change in area responsible for some kind of enhancement of the efficiency. In the second part of the study, uh, what we have done is that now we have taken 4 sudden contraction setup. Okay, and then we have taken this one that is mentioned at G1 throughout hydrophobic. So these are glass tubes, glass capillaries. We have coated them with PTFE coating. So and made them super hydrophobic. Okay, hydrophobic of 167.2 degree of contact angle. So throughout. Then the second one, we remain it as a glass tube only. We haven't coated it. So this is hydrophilic tube of glass. Third one, upstream is hydrophilic, downstream is hydrophobic. Fourth one, upstream is hydrophobic, downstream is hydrophilic. So what is the idea? All 4. So from the first study, we concluded what type of geometry is enhancing. From the second part of the study, we are trying to see what combination of wettability can induce further local turbulence in the setup, okay, which could enhance the mass transport. And for a comparison, we keep these 2 things. Okay, we haven't changed the contact angle abruptly. It is one is hydrophobic, one is smoothly homogeneous hydrophobic, homogeneous hydrophilic, and there is a change. Okay, in both ways. So we want to study what kind of combination giving me the highest kind of mass transfer possible. So in this study, what we have done, so this is the first one that we can see. So these are the these are the contact angle that is mentioned. Okay, and this is the flow pattern map. So G1, G4 upstream, G1, G4 both are having hydrophobic upstream. Okay, G1 is continuous. Okay, G1 is which one we are calling G1? This one. It is remain hydrophobic only. Fine. So what is the flow pattern? You can compare from here. AS is aqueous slug and AD is aqueous drop. Basically slug and drop. Since we could have seen two different slug formation, one is the slug is made of toluene and another is made of aqueous. So AS and AD are the nomenclature is like that. Since it is a hydrophobic material, so water is in dispersed phase and the organic phase is in the continuous phase. So this is our flow pattern map. So if it is remain that way, only thing changes is a sudden change in area. So what will happen? Happen is that we have slug droplet formation enhancement, and that's all. Okay. When we have a change of wettability combined with the change of area, then what happened? We get entirely different set of flow regime. So here we have air aqueous slug and aqueous drop. Here we have organic phase slug and encapsulated aqueous slug. Okay, so so this encapsulation is a new thing that we are seeing. So this is water droplet encapsulated inside the toluene one. So this is so new flow regime, altogether new flow regime is being not only appeared but also occupied a dominating part of the flow pattern map. Okay, so this is what happened when you combine uh, things together. Only change in the area giving you same type of flow regime with some change in shape or formation of additional drop. When you combine it with a change in contact angle also, you will end up with almost new flow regime map with dominating flow regime is some other type. Okay, encapsulation we haven't seen till yet. Okay, so this is the result of change in sudden wettability. G2, G3 upstream. So this is hydrophilic upstream and G2 is continuous. Okay, only change is the change of area. So what we are observing? Organic slug, organic drop, with organic drop again occupying the main flow regime map and formation of dotted droplet in this regime. Okay, in this part. And here again this reverse phenomena is happened. Aqueous slug formation and encapsulation formation. And with encapsulation formation is the dominating flow regime. Okay, so with this much of understanding for this one, let us now look at what happened when we have what is the effect of this change on the extraction efficiency. So this is our G1, sudden contraction hydrophobic, all homogeneous hydrophobic. So this is my extraction, highest extraction efficiency is around 80%. So sudden contraction hydrophilic efficiency slightly enhances. Any reason? Any reason? What is the difference over here? They are all homogeneous. One thing is hydrophobic, one thing is hydrophilic. And we have seen that in hydrophilic, there is an enhancement of efficiency without doing anything, any change in contact angle. They are homogeneous. Okay, why so? Yes, absolutely. So in the second case, it is hydrophilic one. So water is continuous media, and we have slugs of toluene having much low viscosity than the continuous medium. Always the viscosity is around half. Okay, so the circulation, even that we have observed through our simulation, I have shown you, if you recall, in my second lecture. Okay, the circulation inside a low viscosity slug is always higher, and that is the reason why we are getting higher efficiency in this case. Okay, it is easy to form circulation when the media, when the dispersed phase media is of low viscosity than of high viscosity. Okay, for obvious reason, it can be, the shearing effect is higher for the lower viscosity dispersed phase. So this is the first observation. Second observation, let us see. So this is sudden contraction, hydrophilic to hydrophobic. And this is sudden contraction, hydrophobic to hydrophilic. Which one is higher? Obviously this one. Okay, what could be the reason?
Section it will cause more cell encapsulated. So
No, this one, what is marked, actually encapsulation, what we have observed till now, when things are getting inside and they are encapsulated, we haven't seen enough mass transfer on such structures. Okay, so it is the aqueous slug and droplet only for the this one, first one. Okay, at the, so okay, no, this is the upstream flow regime. Mark on the upstream flow regime. Yes, downstream you can get such kind of encapsulated one, though they are not very preferred kind of thing in with respect to mass transfer, but obviously they are preferred for some other application, right? So why the efficiency is higher from sudden hydrophobic to sudden hydrophilic? We get higher efficiency here also, but this is very high. Okay, so what could be the reason? Again, we tried for numerical simulation to get the answer. Okay, so when we do that again, so this geometry is similar to other that geometry that we have taken. What is we change here is the contact angle of upstream and downstream. Okay, rest is same of the other simulation. Again, we go for validation. Then this is the case what we have studied. Okay, so this is the slug, this is hydrophilic, and this is hydrophobic. Okay, so this is a formation of slug in the hydrophilic one. So this is toluene slug. Okay, so blue one are the toluene one. So when it enters, what happened? You can see there is a pinch off that is happening. When the pinch off happens, it forms a small drop, and this small drop is now being inside of this red one. Okay, so hydrophobic section, red one, is nothing but water, a long slug of aqueous with a small drop of toluene inside it. That is precisely what we call encapsulated slug. Okay, so when such thing happens, as I say, the mass transfer in such cases are not that much of enhanced, but and there is also another thing happen, that there is, we could see very little of any disturbance wave or the film thickness over here. So in this case, what will happen? So this is hydrophobic. Okay, so this is water drop, it is broken up, when it enters a hydrophilic section and it forms a continuous phase, and you have toluene drop that are forming. Okay, so with toluene slug that are forming, there is always presence of this one, this disturbance wave that we have seen earlier also. So this disturbance wave is again responsible for enhancement of the further improvement. Also, what we have seen, let me see, yes, this one. So when they have encountered a sudden change in the area, so there is a formation of this kind of a stagnant regime. Okay, so there is a stagnant and recirculatory regime observed here. So this is this marked by, this is the phase contour and this is the velocity contour. So uz is the dominating velocity in this direction. So the blue one, what you could see is the negative velocity. That means there is a backflow. Okay, there is a recirculation region, even if there is a stagnant region also. So it's a backflow, a stagnant regime gives you kind of rotational presence of any rotational circulation over here. So this type of circulation enhances further mass transfer. So this happens when one phase, this is the effect of sudden change of wettability. So one phase when you introduce, okay, and that phase need to be retracted, because here there is a phase inversion is happening. So in this part, this is this slug, or the slug is basically broken down and forming a continuous phase. So this blue part over here, which is forming slug, as it enters and feels there is a change in wettability, the moment you can see there is a presence of a continuous medium, and gradually the continuous medium over here are forming the dispersed medium. Due to this role reversal at this point, okay, and also, of course, there's the presence of vena contracta. So what happened? You can get to see a recirculatory zone which further enhances the formation. Also, with the fact that why we are getting so much higher efficiency in this one from hydrophobic to hydrophilic is that not only this, not only the presence of this circulation, but also presence of this disturbance wave which are unique to a low viscous dispersed slug, which are further enhanced by this presence of such kind of thing. We have done the simulation for G3 also, I mean, that is hydrophobic. But in this case, viscous media is forming the slug, and these disturbance waves are not observed. Okay, the dispersed media is able to resist such kind of changes. So what happened? Your disturbance wave that are present in this case, okay, and the disturbance wave, if you recall, disturbance wave, what I have shown you earlier, that in this type of waves, there is a presence of recirculation. Okay, so in the film region only. So this recirculatory presence, along with the presence of a recirculation over here, these two phenomena giving you highest efficiency for this particular setup, okay, which has a hydrophilic downstream. You can conclude or generalize in a way that a sudden contraction can obviously enhance the mass transfer, and if there is a change in wettability, so it is when you have to, it should not be, I should say that in terms of hydrophobic or hydrophilic, it is kind of if you take a sudden contraction, you have to look at what are your phases and which is your viscous media, which is your low viscous media. So if you wish to have a slug of low viscous media, what will be your contact angle of the solid wall, that you have to figure out. So you have to design in that way. So you have to, for our case, we can say it's hydrophobic and hydrophilic. We have taken water and toluene. Okay. So maybe you are taking other solution. Okay. Maybe you are taking some other operation or some other targeting some other reaction or some other mass transfer operation. Your material is different. So, but the idea is this is can give you some idea that how to proceed. Okay. So what the takeaway from this one is that what kind of combination could enhance your mass transfer further. Okay. And always we have to keep in mind that it is not only the enhancement of the transfer process, mass transfer, that is our final motive. Obviously, when we design, we need to keep several things in mind. So it is the efficiency, of course, the main objective, but how to optimize the design so that you can enhance your transfer rate with a minimum input from energy. Okay, or minimum enhancement of energy consumption. So this is further modification that we have done, and this is the final observation. So if, as I say, so two things we have done. One is the phase inversion. Second is the circulation zone that we have observed due to this phase inversion. This observation of this circulation zone is not there when we don't have this kind of phase inversion. And then in the downstream, if we have the circulation region followed by the less viscous phase is forming your dispersed phase, then probably you could get some disturbance wave at the interface. So combining these two effects, you can further enhance the mass transfer. Okay. So at this point, I would like to ask you if you have any doubt. Mm.
So one is the wavy nature.
Mm.
So wavy nature is to contribute that part. Was already there in the both hydrophilic section. So when bromine was entering the hydrophilic, then also it showed the wavy nature. But then the enhancement was not that high.
No, toluene, when the toluene is entered in the hydrophilic one, okay, so if it is homogeneous, I mean, if you compare the tube to be throughout homogeneous means 2 mm upstream is also hydrophilic, 2 mm downstream is also hydrophilic. So it is toluene dispersed in the upstream also and toluene dispersed in the downstream also. In that case also we have seen the disturbance wave. Okay. Yes. So
Was not that high because of that.
that because later if you change the weightability, in addition to that disturbance wave, we have what type of flow regime we have at the lowest. So the type of regimes also matters when it comes to that low Reynolds number, this type of thing. So this is organic phase Reynolds number is very less. Okay, very true. And the aqueous phase Reynolds number is also less. So eventually, yes, it is spending more time. That is right. Right. But that structure of slug, okay, and in mass transfer or any reaction, the molar ratio also matters. Okay, for any mass transfer, there is a limitation of the mole. Okay, so that effect is there. So this is spending much time. That is very true. But at the same time, what you can expect, there is no disturbance wave like that what we have observed that is present because of less interfacial interaction. That is one. Second is that the molar ratio for the extraction is also not in favorable position for such low aqueous and Reynolds number uh, cases for this particular cases. Okay, I don't recall exactly, but we have carried out this exercise to figure out what is the optimum molar ratio for such kind of extraction. So we have that data. If you wish, I could send you or give you the reference. You can look at. So yes, there are. So that is what I am telling. So it is not only one factor that is giving you the idea. Or minimum kind of any transfer rate, whether it is reaction or mass transfer, governed by two logic. One is the specific area of contact. Second is whether there is any, what is the minimum residence time. Then whether is, because if you recall the in such cases, the transport process is governed by molecular diffusion. So any molecular diffusion is a slow process in that way. So if you don't have any circulation, okay, any disturbance, so it is eventually become slower. And on top of it, there is some limitation of the molar ratio also playing a part. So that is why these are not a favorable condition to carry out the extraction. And this is true for every other geometry. There is no effect, absolutely no effect of geometry in these lines, in these operating conditions. Okay.
So one last question. Mass transfer here occurs from the organic phase to water phase. And we observed that for water there was no wavy structure because of higher viscosity compared to polymer.
Yes.
So despite the fact a wavy nature was not there, the mass transfer still increased only when it was there in the organic phase. So let's say we reverse the case that we have solute now in aqueous phase and it has to be going to organic phase. Do you think we will still get the same result?
So if you are solute in organic phase, sorry, in aqueous phase, so possibly the reverse phenomena then in that way giving you more result. I'm not saying the exact same test section will provide you the same one. Okay, because then you have to see what is the possibility of combination of wettability, because the always what would happen, the reaction or mass transfer is happen at the interface. Any disturbance wave production at the interface will be enhancing. Okay, so in that way you can think of probably the interfacial phenomena will be benefited from any formation of disturbance wave. Now you have to see between G3 type of geometry or G4 type of geometry, which one will be your beneficial one. Any other? In a single, yes, it is very much possible. And in fact, this is the, I mean, motivation for our work to do it separately. If you go back to literature, we have found that researchers have used a series of sudden contraction and sudden expansion. okay, in order to enhance either mixing or mass transfer or reaction. So this is kind of uh, this much of reactor diameter, suddenly it is getting enhanced, suddenly it is getting lowered, suddenly it is, so there is a series. Okay, so our objective is to understand whether we need so much of, series of contraction expansion, or the limited number of contraction and expansion can do the work efficiently. Okay, so yes, it is very much possible, but it is always advisable to optimize the thing.
Would the effect of in hydrophobic section small and large length of that would also have impact on this phenomenon?
Yes, length.
Right now we have taken 1:1, means both are equal length.
Yes.
We change the length individual section.
Yes, yes, yes. To a certain extent, definitely it will have the effect. And after a certain length, as I have seen in the last one, for this one, we haven't optimized the length in that way. But yes, of course, there should be optimum length. Okay, after that optimum length, you can have a less amount of transfer possible. Okay, I mean, you achieve closer to the equilibrium when you don't need any more length with giving you higher values. So yes, that is another very good suggestion to follow. We haven't tried with this one till now. We haven't varied the length because we don't want to vary the length in this particular situation, as our focus is on something else. Okay, but with the length, definitely there should exist some kind of optimization.
How much do you think the large section would be contributing to the overall transfer and the small section, or both are contributing equally as of now when the lengths were equal? Would they be contributing?
See, that is very qualitative answer to give, because we are not measuring the efficiency lengthwise. We are just measuring the efficiency at the end of each unit. Okay, so how much is the contribution for the first one and how much is the contribution is the second one? One can only tell if we have the sample after, let's say, one segment, and then we have the sample for other segments. So what is the contribution in that way, or whether it's linear or not, that I have the data for 80 centimeter, so I can say you the, okay, 40 centimeter is this efficiency. I don't think that is very linear thing to follow. So we don't have some such, because it's a continuous reactor, we don't have any intermittent data for that matter. So length contribution, okay, or individual unit contribution, we cannot ascertain from this analysis. Yes, you can, again, if you vary the geometry or the cross section, it will somehow contribute to first to the hydrodynamics. Even if you take some different inlet also for that matter, it will give you some kind of different hydrodynamics to certain extent. Okay, and these are, of course, you need to test that how much is the contribution if I vary the inlet configuration, if I vary the shape, okay, if I vary the hydraulic diameter, so what will be the contribution? That is another of course there is a contribution, because there are all the parameters that are going to influence the hydrodynamics and which eventually influences any transfer process. So there would be a thing, but how much is the thing and how, in what way it is contributing, that is you need further investigation on that. Okay, is anything else? Okay, so thank you. All the lectures are now covered. Okay, please join for the tutorial after lunch at 2:30 and at the CAD lab.